Let us have a look at the electric field because of various charge configurations. So here we have a ring of charge. This particular ring of charge has a charge Q uniformly distributed on it. So this is the ring on which the charge Q is uniformly distributed. Now this ring has an axis, and this axis is a line that is perpendicular to the plane of the ring and passes through the center of the ring. Now on this axis we have got this E perpendicular right over here. This E perpendicular is exactly what we are going to find. Because of symmetry considerations, any E parallel in such directions will be 0 because the axis is symmetric with respect to the ring. E perpendicular, we will note, is also perpendicular to the plane of the ring. The distance at which this point P is present, wherein we are noting down the expression for E perpendicular, is x. So the expression for E perpendicular happens to be 1 upon 4 pi epsilon naught qx upon x square plus r square raised to 3 by 2. So this is the expression, and we need to know this expression by heart. Here we also see a graph that is plotted. This is the origin, and the graph of this particular expression is plotted. We can see that it has a peak and then it goes down to 0. If we put x equal to 0, we can clearly see that E perpendicular is going to be equal to 0 for x equal to 0. This is clearly apparent. Also, if we put x equal to plus infinity or minus infinity, E perpendicular again is going to be 0. So E perpendicular equal to 0 for x equal to plus minus infinity. This also is understood. So here we get the plot that goes to a maximum and then again goes down to 0. We can see that using the methods of differentiation, we can find out the maximum value occurs at r root 2. X equal to r root 2 gives us the maximum value of E perpendicular. Similarly, on the negative direction of the x-axis, we get the maximum at x equal to minus r root 2. So these are the two values of x for which we get the maximum value of E, and this can be shown via methods of differentiation. Now this is a disk of charge. Earlier we dealt with the ring of charge. Now this is a disk that has charge. So this disk will have certain thickness, which is also negligible, but this disk will have a certain amount of thickness. Now this particular disk will also have an electric field that is perpendicular to the plane of the disk and present on the axis. This is that particular electric field E2 that is perpendicular to the plane of the disk and present on the axis. So the value of this E perpendicular happens to be equal to sigma upon 2 epsilon naught 1 minus x upon a root of x square plus r square. And herein x happens to be the distance from the center of the disk to the point P, wherein we are writing down the value of E perpendicular. Again, because of symmetry considerations, any E parallel will be 0 and there will be no E parallel component involved over here. Only and only component that is present on the axis is the E perpendicular component. So this is a disk that has a total charge of Q uniformly distributed over its surface. So unlike the ring which was hollow, here the disk is solid. It is a planar diagram, but it is solid. It's not hollow unlike the ring. Herein we have an infinite sheet of charge. So for the infinite sheet of charge, we have E perpendicular to be equal to sigma upon 2 epsilon naught. In fact, if we put the value of R as infinity over here, then we can see that the second term actually dies down and goes to 0. Hence we are left with sigma upon 2 epsilon naught. If the value of R is infinite, then in fact we get an infinite sheet of charge. So this is the infinite sheet of charge that we are talking about. So the value of E perpendicular is sigma upon 2 epsilon naught, and we will notice that curiously this value of E perpendicular is independent of x. So since this is independent of x, this is a constant value. So whether we are closer to the infinite sheet or further away from the infinite sheet, it doesn't really matter. The electric field perpendicular to the infinite sheet is going to be sigma upon 2 epsilon naught. And because of symmetry considerations, the electric field parallel to the sheet is going to be 0. Let's have a look at an infinitely long line of charge. So this is a line of charge that is infinitely long. Because of symmetry considerations, again E parallel is going to be 0, because if we say that E parallel will have a component in the upward direction, then we'll say that why not in the downward direction. So these are called symmetry considerations. Because of symmetry, E parallel is going to be 0, because upward portion is exactly symmetric compared to the downward portion, and hence what will be left with is only and only E perpendicular like this over here. So this E perpendicular is going to be equal to lambda upon 4 pi epsilon naught r, and E parallel, as we have mentioned, is 0. R is the perpendicular distance from the point in consideration to the infinitely long line of charge. Let us now have a look at a finite line of charge. For a finite line of charge, the finite line of charge has certain limited dimensions. So instead of measuring the length, what we do is we measure the angle alpha and beta. Note that this distance, the perpendicular distance from the point in consideration to the finite line of charge, this distance we are taking as r. So r is this particular distance. The perpendicular electric field is going to be lambda upon 4 pi epsilon naught r sine alpha plus sine beta. This is going to be the perpendicular electric field. And the parallel electric field is going to be lambda upon 4 pi epsilon naught r cos of alpha minus cos of beta. Here the important thing to be noted is E parallel has been taken towards alpha side. So if we had taken E parallel to be towards the beta side, then here we should have written cos of beta minus cos of alpha. Since we are taking E parallel to be towards the alpha side, that's why we are writing cos alpha minus cos beta. Let's understand that. And that is the value of E parallel, lambda upon 4 pi epsilon naught r cos alpha minus cos beta. Let's understand this. So for a finite line of charge, E parallel is non-zero. This needs to be noted. Unlike an infinite line of charge, wherein because of symmetry considerations, E parallel turned out to be 0. Let's look at a charged spherical shell. So inside the shell is hollow. Because of something called as Gauss law, we can draw a Gaussian surface which has net zero charged enclosed, which we will study soon. Because of that, inside this hollow spherical shell, E is going to be identically 0 for r less than capital R being the radius. And outside the shell is going to be equal to 1 upon 4 pi epsilon naught q divided by r square. This is for all the points outside this particular spherical shell. So for r greater than equal to r, we have E outside as 1 upon 4 pi epsilon naught q divided by r square. If we plot this on a graph, on the x-axis, we are plotting r, the distance from the center. Here we have this point wherein r is equal to capital R, the radius, and on the y-axis we are plotting the electric field. So inside the electric field is 0, that's why we get this value. Then we get a sudden jump. This particular value of the electric field will be 1 upon 4 pi epsilon naught q divided by r square. This will be the value at this point. And after that, we get a decline, an exponential decay like this, and at infinity it goes down to 0. So this charged spherical shell, when we are looking at points outside the spherical shell, behaves just like a point charge. And for points inside the spherical shell, E inside is going to be equal to 0. Let's look at a uniformly charged solid sphere. So for a uniformly charged solid sphere, it is very important to note that outside the sphere, the expression remains the same. 1 upon 4 pi epsilon naught capital Q divided by R square, where capital Q is the charge of the entire sphere. For points inside the sphere, we have written down this electric field in a very easy to remember manner. It is 1 upon 4 pi epsilon naught Q divided by R square, which is like the electric field at the edge. This is actually the electric field at the edge, into R upon R, where small r is the variable distance from the center. This would be small r, let's say, and capital R happens to be the radius. So this is a very easy to remember method, and we can see that for the values of small r less than equal to capital R, we have linear proportionality, because only small r is the variable over here and everything else is a constant, and hence in the graph, when we plot the graph, we get E inside is proportional to R. We can see that at the surface, the expression for electric field inside as well as the expression for electric field outside, both are going to give the same value. So at the surface, we just put small r equal to capital R, and hence we get these two cancelled, and this is the expression at the surface. Similarly, if we put small r equal to capital R over here, then also we are going to get the same expression, and the expressions will match at the surface. So there is no discontinuity over here. At the surface, at small r equal to capital R, the expressions of the electric field inside as well as the electric field outside are matching. We can then see that for outside points, electric field E out is simply going to be proportional to 1 upon R square, as per this expression that we have mentioned over here.